Okay, good morning. We continue our lesson in matrix theory, part 7 this time. If we learned how to multiply a number by a matrix, we learned how to add two matrices, subtract them, and finally we also learned how to multiply matrices. And we actually discussed a lot of things in matrix multiplication, which was the first deviation from number algebra. Now today might be you can predict yourself that we want to talk about powers of matrices. So I give you a matrix and I, for example, ask you to raise it to power 2 because powers are actually a natural consequence of products. Yes, so you remember the reason that we invented the notation, power notation, in the first place, because we wanted to summarize long products of a number by itself. For example, if I have number a and if I multiply it 4 times, so instead of writing it in that form, I would write it a to the power of 4. Yes? So this is just merely a symbol, a shorthand notation for this longer product. So what I'm saying is that the powers are actually coming after we have multiplication. Now that we have settled down matrix multiplication, might be this is not very surprising that you need to the next step would be talking about powers of matrices. Okay, but the first thing that you need to be careful when you want to talk about powers of matrices. For example, let us just talk about the simplest power of 2. Okay, so this means that I want to multiply the matrix A by itself. So if A is a rectangular matrix, say m by n, then what happens if I want to multiply an m by n matrix by itself, which is that one is also m by n because these are the same matrices, then you immediately realize this is not possible because these two numbers has to be the same. Okay, so it means that if I want to define a power for a matrix, m and n should be the same. In other words, the number of rows and number of columns should match. So in other words, it should be a squared matrix. So this is something that I want you to know. You cannot talk about powers of matrices if matrices are really rectangular. They have to be square matrices so that you can talk about powers. Yes? Okay, so this is why in my definition of non-negative integer powers, okay, of a square matrices. So that's also a long story. What can I say about a to power minus 2, for example? Is there any meaning for a to power 1/2? Of course, we will not touch these things. I don't know how much time we will have. Might be we will come to that point that we can also talk about negative powers of matrices. But for the time being, we just want to concentrate on the exponents, which are non-negative and integer. Okay, so 0, 1, 2, 3. These are the only numbers that you might see as the exponent of a square matrix. I'm just talking about these things, and I think that you already know the answer and the definition. It's the most natural definition, yes? Let A be a square matrix of order m, so a square, and let n be a non-negative integer. The nth power of A is denoted by, as usual, a to the n, and it is defined inductively or recursively as follows. If you see a to the 0, by the analogy that we have for numbers, we define it to be the identity matrix. Yes, if I have a number, a to the 0 is defined to be 1. 1 was the identity element in matrix multiplication, so that this IM is playing the role of 1 in numbers. So it's natural to define it in that way. And be careful about this index, because I told you that A is an m by m matrix. So if you write a to the 0, it becomes the identity matrix of the same order. And of course, if you want to calculate or define a to the n, if n is greater than or equal to 1, what you do, you define it as a multiplied by 1 power less. So it means that if I want to calculate a0, by definition it is I. If I want to calculate a1 is a multiplied by a0, but a0 is I. So that is what expected, so a to power 1 is itself. If I want to calculate a2, I need to multiply a by the previous power, which is a. If I want to calculate a to the 3, I need to multiply a by a squared. But then, of course, this list can continue. So this is a very simple definition. And then might be, so let me just do this example very quickly. So consider the following matrix, determine a squared. So it means that if I want to determine a squared, what I need to do, I need to use the definition, meaning that a should be multiplied by itself. And then it means that I have to multiply this matrix by itself. Okay, and then hopefully this is a very simple exercise for you by now. If I calculate, let me go below, I have enough space. So here I have to take this row, multiply it here and there. So the answer to the first one is 4 plus 4 is 8. Please correct me if you see I am making mistakes. And the other one is minus 2 minus 3 is minus 5. The other one is minus 8 minus 12 is minus 20. And the other one is 4 plus 9 is 30. Do you confirm my calculation?
I got the same.
Okay, good. So what you see is that in general, it's far away. Please don't fall into this trap that if you want to square it, go and square these entries. If I do that, I will get 4, 1, 16 and 25, 4, 1, 16 and 9. Okay? If I want to square them individually, what I get is this block of numbers, but the correct one is this block of numbers, even they don't have one single entry in common. So be very careful. When we talk about powers, it means, as usual, multiply the matrix by itself. Of course, these are obvious things. Powers of a non-square matrix are not defined, so as I discussed in the beginning. If 0 is a square matrix, this is the 0 square matrix. For every non-negative integer n, of course, it is very clear that if I raise the 0 matrix to power n, it becomes it. This is also another similarity between matrix algebra and the number algebra. And if I is the identity matrix of any order, I hope that this is clear for you, that I to power n is itself. Because I2 is I times I, but we learned that every matrix, including I itself, multiplied by I becomes the matrix itself. So when a squared is I cubed is also I, you can continue. Of course, if you want to prove it rigorously, you have to use mathematical induction. But these are very trivial things, okay? Please interrupt me if you have any questions. Okay. Here, this is another example. Consider the following matrix, and then we want to show that a to the power 3 is equal to the 0 matrix. You see, this is the difference of algebra of matrices and algebra of numbers. This is not possible in numbers, yes? When I have a number a to power 3 equals to 0, it's inevitable. This implies that a is itself equal to 0. But you see that in this matrix, even I do not have one single 0 entry, but its third power suddenly becomes the 0 matrix. And you will see that the second power is still not the 0 matrix. These kind of matrices, studying of these kinds of matrices is beyond the scope of this lesson, but these are called Nil Potent Matrices. So a matrix which is not the 0 matrix, of course, and there is a number that you raise it to that power, the matrix itself becomes 0. This is not guaranteed that every matrix has this property, but Some matrices have, and if the matrix of this, if there is a matrix of this type, it's called a nilpotent matrix. Okay, but here we want to show that this is indeed the case. So what I have to do, I have to calculate a to the 3. So these are very simple, but you need to do them patiently. So for a to the 3, I will calculate a to the 2 first. So it means that I have to multiply a by itself. Then it means that I multiply 1, 1, 3, 5, 2, 6, minus 2, minus 1, minus 3 by itself. Yes? Okay, so if you do the first one, so I do this and then you can do it yourself, and if I am making mistakes, please tell me. So what I am doing, I am dividing the left hand side to rows and decomposing the right hand side to columns, and I multiply each row by each column as usual. So 1, 5, 6 minus 6, I get this one to be 0. 1, 2, 3 minus 3, this is still 0. 3 and 6, this is 0. And then I have 5, 10, 15, this is 3. 5, 9, 3. 15 and 12, 27. 15 and 12, 27, so this becomes 9. This becomes minus 1, and the other one is minus 2, minus 2, minus 4, plus 3, minus 1, and then minus 6, minus 6, minus 12, it's minus 3. Do you agree with my first calculation? May you speak louder, please?
So far, yes, not
Okay. Okay, so I can also double check. So I took this one and multiplied that here. So yeah. So you see 1 is 1, 1 times 2 is 5, 3 times minus 2 is minus 6. If I add them, it becomes 0, and I did the same thing. Okay. So let me calculate a3, but a3 is what? Is a times a squared. But a is this original matrix 1, 1, 3, 5, 2, 6, minus 2, minus 1, minus 3, and I want to multiply it by a squared, but a squared is the matrix I got just right now. So it's not a trivial question to cook up these things. I hope that I haven't made any mistakes when I was designing the question. So let me check. I take this one and multiply it here. So if I am right, every entry should be 0. So 1 times 0 is 0, 1 times 3 is 3, 3 times minus 1 is minus 3. So that's so far so good. So this is 0. I will take this one, multiply it here. So it becomes 0 plus 3 minus 3. So that's good. This is also 0. Then I will take this one and multiply it here. So it becomes 9 minus 9. That's also 0. Then I will take this one and multiply it here. So it becomes 6 minus 6. Good. This is also 0. Take this one and multiply it here. It becomes 6 minus 6. That's also 0. I will take this one and multiply it here. 18 minus 18. Good. So we are lucky so far. Okay, and then I go here, take this one and multiply it here. Minus 3 plus 3 is 0. And then I will take this one, multiply it here. Minus 3 plus 3 is 0. And then minus 9 plus 9 is 0. Yes, so we did it correctly. And this is the 0 matrix. And at least, hopefully you are convinced it is not trivial calculation at all. So you see, when I multiply it 2 times, of course I got a bunch of zeros, but most of the elements are still not 0. But the third one, suddenly they are designed in a way that for the third one all the entries become 0. So it means that this matrix is equal to. Let me ask you one question. Can you tell me what is a 1000 now?
Zero.
Yeah, it is the 0 matrix, because a 1000, so what is coming after a4? A4 is a3 times a, but a3 is 0, so 0 times a is the 0. So it is clear that any power after 3 would be 0, yes. Okay, so this is, I just want to see by this example, even this is a 3 by 3, it was not trivial at all that how these entries are behaving, so that at the end, after 3 times, all the entries turned into the 0 entry. Okay. If you don't mind, I want to wait a little bit for you that you can solve the other problem. These problems are simple, but you need to train yourself to be a little bit fast in these kinds of calculations. So I pause the video at this point and I want you to solve this problem yourself first. Solving the problem, I think you know what to do. So I would start, I would start from writing this identity. And so this is not identity, sorry, this equation or whatever. I am going to find alpha and beta. So what I do, I will write a squared means a multiplied by itself. On the right hand side I have alpha, I have matrix A. Yeah, please watch my calculations. So then beta, this identity matrix, it is clearly a 2 by 2, otherwise this sum is not defined in the first place. Okay, so but what I need to do, I need to multiply the first one, so it becomes 5, 4, 4, and 5. If there is something you don't understand, please let me know. I multiply alpha, which is a number inside, so that's a very old lesson, how to multiply a number by a matrix. And then what I do, I will get beta 0, 0, beta. And the next step, I will repeat the first one. I will add the right hand side, so it becomes alpha plus beta, 2 alpha, 2 alpha, and alpha plus beta. So even though I get 4 equations, but 2 of them are the same. So what I just need to write is alpha plus beta equals to 5, and 2 alpha is equal to 4. I have 4 equations, of course, but they are repeated, so I don't bother to write them down. So as you predicted, alpha is 2 and beta is 3. So yes, alpha is 2 and beta is 3. Good. Please let me know if you have questions. Now we go to the next one. If you don't mind, I want to wait for you for this problem as well. So consider the following matrix. Determine x if the entry on the third row and second column of a to the 3 is 72. Whenever you are ready, you can write your answer on the chat window. Thank you. But even though you can multiply this matrix by itself 3 times and go and find the entry on the third row and second column and equate it with 7 and 2 and find your x by solving an equation, I prefer you learn this method, even though it is not very simpler, but it is simpler. But I want you to learn, because from theoretical points of view it's important. So what I want to calculate is the entry on the third row and second column of a cubed. But today we learn that what is the meaning of a cubed? It is a times a times a. By the way, if matrix multiplication is not associative, we are not able to define this, because if it is not associative, who knows that this matrix and this matrix are always the same? But we know that they are always the same because matrix multiplication is associative. So here there is no ambiguity if I write it in this way, but that is up to you how you want to collect them. So if you don't mind, let me take the first two as one matrix and the third one as second. Okay, you don't need to write so much, but because I am explaining, I want to make sure that you understand everything fine. This is why I'm explaining so much. But anyway, if you remember, there was a formula. If I ask you what is the ith row of a product, matrix M by matrix N, do you remember? This is important from theoretical points of view in matrix theory. So what I would say, this is the ith row of the matrix on the left multiplied by the whole matrix N. And if I ask you what is the jth column of the same product, you would say that you will take the whole matrix M and just multiply it by the jth column of matrix on the right. I want you to learn these things. So of course this is the only thing what we need, but let me just write it here. If I ask you what is M times N, Ij, of course you have a formula using sigma, but there is also something good to know. You take the ith row from the matrix on the left and just multiply it by the jth column of the matrix on the right. So that is also something I want you to know. These formulas are important in matrix theory, so let me just group them. Here we don't, of course, here we don't need the third one, but let us for completeness write all of them so that by time you start learning them. Okay, so here I want to use the first and the second one. So how should I consider? In my head I can consider this the matrix M, and I can consider this the matrix N, and I am interested in the third row and second column. Oh, by the way, I need this one, sorry. We need all of them. So this becomes equal to R number 3 from matrix M, but matrix M is A times A, multiplied by the second column of matrix N, but matrix N in this case is A. But now this is another product here, and I am interested in the third row. So I have to use this first formula once more. So what happens, it becomes the third row of A multiplied by the whole matrix A, and after this is done, I have written it here, you see this is coming. So I have to write this here, C2 of A. So what I should do now, I only need to take the third row of A, which is this one. So X minus X and X, and I have to multiply it by the whole matrix A, which is X minus X, X, and then I have to multiply it by the second column of matrix A. But if you see what is the second column, it is easy to read it from the matrix itself. It's a little bit easier. You see, if you don't want to pay attention to this, this should be a 3 by 3 matrix, this should be a 3 by 3 matrix, this should be a 3 by 3 matrix. So you have to do some calculations which are indeed not necessary for the purpose of this problem, yes? Okay, so what should I do? What I prefer, it doesn't matter if you multiply this by this one first and multiply the result here, or keep it on the left hand side, multiply these two first and then multiply this from the left to the answer. Okay, I myself always, because I don't know, because most of the time in linear algebra we are facing a matrix multiplied by column matrix, so I have trained myself here so I can do it faster. So let me write the first part, X minus X and X, and then I multiply it these two matrices. So this is a 3 by 3 matrix, this is a 3 by 1 matrix. Is it possible to multiply? Yes. What would be the result? The result would be a column matrix of order 3. Okay, so I will take this one and multiply it here. The first one by the first one gives me minus x squared. The second one by the second one gives me minus x squared again. The third one by the third one gives me minus x squared again. And if I add them, it becomes minus 3x squared. So the first entry is minus 3x squared. Okay, now I realize that I think you are correct, actually. So I lost you. You didn't write something here. I think your answer is correct, Eric. So here it would be the other one, because I didn't consider these trees for some strange reason. Okay, so anyway, so I have to take this one and multiply it here. This becomes x squared, this becomes x squared, this becomes x squared, yes? And then I add them, I get a 3x squared. And then I will take this one and multiply it here. It becomes negative x squared, negative x squared, negative x squared. If I add them, it becomes negative 3x squared. Yes, I remember something when I wanted to design. I didn't want to have that very strange number up there. Okay, now what I do, I multiply this matrix, which is a 1 by 3 matrix, this matrix, which is a 3 by 1 matrix. It is doable, yes, they are cancelled, so it becomes a 1 by 1 matrix. And you know that a 1 by 1 matrix is identified with the entry itself. So what happens? I multiply this by that one. It gives me minus 3x cubed. The next one is also minus 3x cubed. The other one is also minus 3x cubed, and I have to add them. So you know that. Yes, I multiply this by that. I multiply this by that. I multiply this by that. And at the end, I have to add them. So it becomes negative 9x cubed. But on the other hand, this is mentioned that this is supposed to be 72, yes? So this becomes 72. If I divide by 9, x cubed becomes minus 8. Yes? And then clearly x is equal to minus 2. Okay? Any questions here? So, Carl Eric, so your answer was minus 2, yes, or 2?
Minus 2.
Yeah, that's correct. So that was, I don't know, I was careless a little bit. By the way, we can just now go to this Geogebra to see if we can also do it somehow by matrix theory here. So if I want to, might be you cannot see, you can see everything, but everything is not in the recorded screen. But let me just do it quickly. So if you remember, if you want to define matrices, you should define it in this way. So it is x comma minus x comma x, and then I have another one comma minus x, x minus x, and the other one is x minus x and x. So let me see if I have done everything correctly. Yeah. Okay, so I don't see any flaws here. Okay, so if I enter, so hopefully you can see that this matrix is here. But I don't know, might be the syntax is to multiply m1 by m1. So let me just naively type this one. Yes, but it isn't. It hasn't simplified that. This is a little bit strange here. Okay. So I don't know why it hasn't simplified this product. It shouldn't be hard. Any clues? Do you have any clues how we should simplify this? Anyway, but if you go to the third row and second column, so this is the third row and second column. So you see this is the entry here. So it is minus x squared, minus x squared, minus x squared. Oh, okay. We're supposed to raise it to power 3, not 2. So m1 to power 3. Let us see if it works in that way. Yes. But I don't know why. How should I simplify this using GeoGebra? In principle, the answer should be in the simplified version. Is there any simplify? Simplify, yes. So simplify, let me write simplify, and then let me write M3 here. So let me see if it works. No. Simplify only accepts functions and texts. Okay. Okay, there should be a way to simplify that. I haven't worked with this, but you can discover it yourself. It is a little strange. It multiplies but doesn't simplify.
But can't we take the entry that we are interested in and then simplify that instead?
No, yes, of course we can do that, but this is very strange. Why Geogebra doesn't simplify things? Okay, I will think a little bit about that later. You can also do that, but it's very good to learn something to try to see. And I don't know why Geogebra is drawing the graphs of this. This is a little bit strange anyway. Okay, so let us not waste our time and go back and continue. So this is one type of problems that we face. Another type of problems are a little bit more theoretical. So let A and B be square matrices of the same order such that we don't know anything about these two matrices unless we know that AB plus BA is equal to the zero matrix. So you see that this is not commuting matrices because AB is not equal to BA, but the sum of them is the zero matrix. Because we want to show that under these conditions that they are squared and this happens, A squared B is equal to BA squared. So this is another type of problems that could be very hard sometimes. So you need to find a way to prove it using the properties, and you have to respect the matrix algebra all the time. So do you have any clue what to do? So let me just write it here. If you want, I can wait a little bit for you. So we know this is true. Our question is that how can we prove A squared B is equal to BA squared? Okay, so if you don't mind, I want you to think a little bit about this yourself first. Any ideas? This is very, very simple, not hard.
On the previous question to see if I could do it the long way. The first time I got it wrong.
Oh, okay. What about others? Have you thought about this number 5? Because you see that we don't know anything about matrices A and B except that AB plus BA is equal to the zero matrix. So that's completely a generic problem. We don't have any extra information regarding these matrices. But we want to show this. It is not hard. Probably you don't have enough experience now. What I will do, let us do algebra here.
So we prove that AB is equal to the inverse of BA?
No, AB is not equal to BA, as you see.
That's minus BA.
Yes, but then what? Sorry, let me close this window. Okay, so AB plus BA is equal to 0. You know that some part of matrix algebra is exactly like number algebra. So I keep the 0 on the right and I move BA to the left. So as you said, the consequence of this is that AB is equal to negative BA.
Oh, I have an idea.
Yes?
If we use the associativity law and write A squared B as AAB and then substitute.
Yeah, exactly. That is the idea behind this problem. So what you need to do, you can start from the left hand side of what you want to prove. This is A squared B. But today we just learned that A squared is A times A and multiplied by B. But we know that matrix multiplication is associative, so I can write A and I can replace the pair of brackets around the second part. But now here I can use this assumption and then put this here instead. So what happens, it becomes A times minus BA, and then of course you know that this minus sign, it can float around, so I can write it as minus, and then I can write A times BA, and then again I can use associativity. I can put the pair of brackets around the first pair, it becomes AB times A. But now what is AB? Again I use this once more here. Instead of AB I put minus BA, so it becomes minus and then minus BA, and then there is an A. But this minus and minus becomes positive, and I use associativity once more. I remove the pair of brackets from the first pair and put them around the second pair. So these two minus signs actually cancel each other. And then what happens is I have BA squared, yes? And that is exactly equal to the right hand side. So is that understandable? So you see, this is just pure abstract algebra. We don't know anything about matrix A and B except that we know this condition holds. We just showed that if you say this condition holds, based on this analysis, you have to agree with me that this condition also holds. So these kinds of problems are another type of problems, a little bit higher level problems in matrix theory. Is that understandable for everyone? So you see, it's very instructive to learn how these algebraic properties of matrices are actually working all the time. Of course, if you want to do it, let me just solve this with a different color. So you might say that, okay, I want to solve this problem in this way. From this assumption, you can multiply both sides, because you see that your goal is to construct the second power of A multiplied by B, so it will motivate, it will motivate you to multiply both sides from the left by A. That's also possible, but you need to respect the order. And then you can use associativity. So these two matrices are next to each other, so you don't need to spend so much time. I want you to teach these things so you are using them, but you can just do it in your head. So this becomes immediately, it becomes A squared B. And on the right hand side, I have to use associativity once more. I cannot just go in one place. So instead of this one, I put minus BA. This minus sign and that minus sign becomes positive, and this A and that A will be multiplied. So I will get the final answer right. Yes. So this becomes BA squared. This is also one way, but I prefer this method. It's much more organized. We have started from the left hand side, and I have used the consequence of the assumption to reach to the right hand side. Is that understandable for everyone? Good. Let us go now. What is the next problem? This problem is also a nice problem. This is the application of mathematical induction in matrix theory. So if you don't mind, I want to wait for you so that you can complete it yourself. This is claiming that if I give you this matrix, so it's a very nice thing. You see that I hope that you agree with me that raising matrices to powers is an extremely tedious job, especially if the order of the matrix is big. So because every time we have to multiply matrix by itself, and matrix multiplication is a fairly complicated operation. So if we can find a generic formula for the nth power of a matrix, that would be valuable in the theory of matrices itself. So one way of doing that is just try to multiply this matrix 2 or 3 times and hope that you can find a pattern. Of course, studying systematically how we can calculate the powers of a matrix is beyond the scope of this lesson. You will learn it in the linear algebra course in the university. But it doesn't mean that you cannot solve any kind of those problems. So this is one of those problems that you can multiply these 2 or 3 times. You can see a pattern is going on because of this choice of entries, and then if you can find that pattern, you can have an educated guess for the nth power. Of course, this is not a mathematical proof, but that is, you know, the power of mathematical induction. You can use mathematical induction to prove it. But of course here I didn't want to go through those steps. I have just given you a matrix and I have proposed you the nth power of that matrix, and I am asking you to prove that this is a valid argument here. And then probably, even though I haven't mentioned use mathematical induction, but because this is something about a natural number n, you might get suspicious that might be the mathematical induction is useful in this case as well. So if you don't mind, I will pause the video and wait for you to solve this problem, okay? When you are done, you can let me know. Okay, so if we want to use mathematical induction to prove this, so you know that first I need to check this for n equals to 1. So I do not have enough space, so let me just make it a little bit smaller. So n is equal to 1. Then what I do, I would write a to power 1 is equal to, with question mark. I put 1 instead of n everywhere. But we know that this statement is itself equivalent. A to power 1 is just simply 1. And then 1 plus 6 times 1 is 7. The other one is 4, minus 9, and minus 5. And then if you compare it with this given matrix, you see that this statement is true. When this statement is true, this statement is also true because they are equivalent. So it means that this statement is true for n equals to 1. For n equal to k, we assume that this is true. If we choose k, I would say that a to the power of k, we assume that this is equal to 1 plus 6k, and 4k minus 9k, and then 1 minus 6k. So this is assumed to be true. Yes, and now we want to show that the statement is also true for the next step, meaning that if I replace n with k plus 1, I get a true statement. So you need to be careful here. So you need to replace it with brackets around it. But of course, we know that it is better to simplify instead of working with this version. This itself is equivalent to saying that a to power k plus 1 is equal to 7 plus 6k, 4k plus 4, minus 9k minus 9, and the other one is minus 5 minus 6k. So we want to show that this is true. Okay, but you know what to do. Yes, we go from a to the power of k plus 1. So we know that a to the power of k plus 1 is equal to, by definition, is a times a to power k. But a is given from the beginning 7, 4, minus 9, and minus 5. A to the power of k, by the assumption, by the hypothesis of induction, is assumed to be this matrix. So I just write it there. And then what is left for me is just a simple matrix multiplication involving this parameter k. So you know what to do. You need to take this and multiply it here. So what I do, I multiply 7 by the first entry and multiply 4 by the second one. It becomes minus 36k. This becomes the first entry of the first entry of my matrix. The second one, I take this one and multiply it here. So this becomes 28k's. And then I have plus 4 times 1 minus 6k. And then the next one would be minus 9 times 1 plus 6k. and then so you see I am taking this one, multiplying it here. The first one will be multiplied by the first one, the second one will be multiplied by the second one, which becomes 45k, and finally I will take this one and multiply it here, so it becomes minus 36k's, and then I have minus 5 multiplied by 1 minus 6k. So what is left for me is just simplification of this expression. So if you don't mind, let me just remove this a little bit so that I have a little bit bigger space. This is not lengthy. Of course, this will be left for the next session. Okay, so I will continue this here now. I have to open the pair of brackets, so it becomes 7 plus 42k's and minus 36k, and then I have 28k plus 4 minus 24k's, and then I have minus 9 minus 54k plus 45k, and then minus 36k minus 5 plus 30k. Okay, so let us simplify the last step. So here you see that I have 7, and these two can be simplified to 6, so it becomes 7 plus 6k, and here this one and that one becomes 4k, and I have a positive 4, and then here minus 9, and this one and that one is also minus 9, so it becomes minus 9k minus 9, and the other one is minus 5 minus 6k. Okay, and if you compare this with this one that we are supposed to show it is true, you see everything matches, and this means that this is a proof for this. Okay, we have a little bit of time, so let me also talk about this one and make this the final statement. So there is a definition. Is there any question regarding this problem? Okay, so now we go to another definition, the notion of idempotent. A square matrix A is said to be an idempotent matrix if A to the 2 is equal to A itself. For example, might be the most famous one is the identity matrix. Okay, so the identity matrix raised to power 2 is equal to itself. But of course, that's also good exercise. Can you come up with another possibility that A squared becomes A itself? So that's good to know. Yes, so there is. So you might say that okay, this is the identity matrix, but this is not the case. Might be I should be a little bit more careful when I wanted to talk about this. Of course, the identity matrix is an idempotent matrix because its square is equal to itself. But the identity matrix is not the only idempotent matrix. Okay, and by the way, when I am talking about idempotent, of course this should be a square matrix, otherwise A squared is not defined. Okay, so for example, you can imagine a 2 by 2 matrix to see if that is possible to come up with another example of idempotent matrices. So I will leave it open, so that would be a good exercise for you to do it next time. Try to find a 2 by 2 matrix which is not the identity matrix, and it's of course not the zero matrix, because zero matrix also trivially satisfy this condition. Try to find another matrix, 2 by 2 matrix, not the zero matrix, not the identity matrix, but the matrix squared is equal to A. Okay, and then this example, I want to show that if A is an idempotent matrix, the interesting thing is that if the second power of a matrix becomes equal to itself, any power of that matrix becomes equal to itself. Okay, so it's not hard to see it. Let me write and then I will clean this part, because this is not the real solution. But for example, if I ask you what is A to the 3, you would say A to the 3 is A times A squared. But now you are telling me that A squared is equal to A, so it becomes A times A times A, but then it becomes A squared, but again A squared is A. So you see that the third power is equal to itself. If I ask you what is a to the 4, you can say that okay, a to the 4 is a times a to the 3. But we just calculated that a to the 3 is a, so it becomes a times a, it becomes a squared, then again a squared is a. Of course, this is very clear that this is going to work, but this is not a mathematical proof. If we want to prove it, we have to use mathematical induction, yes? So the first thing that we need to show is that, okay, what happens if n is equal to 1, then it becomes a to power 1 is equal to a. I want to use mathematical induction to prove this, and this is true. And now I will assume that this is true for k. It means that a to power k is equal to a, assumed to be true. Okay, and then I want to show that for n equals to k plus 1, this is also true. It means that I want to show that a to the power of k plus 1 is equal to a. We want to show that this is also true. But this is easy again, yes, you agree with me. A to the power of k plus 1 by definition is a times a to the power of k plus 1. A to the power of k. But you are telling me, according to this assumption, that a to the power of k is equal to a itself. So instead of this a to the power of k, I can put a. Then it becomes a times a, but a times a is a squared, but you are telling me that a is an idempotent matrix, so it means that a squared is equal to a, and I am done. So I was able to show that a to the power of k plus 1 is equal to the matrix A itself. So that's a very nice property. If a matrix squared is equal to itself, any power of that matrix is equal to itself. And then this is an open problem for you to think a little bit and give me the answer next time. Can you give me a non-trivial idempotent matrix? Trivial ones are the 0 matrix, because 0 to the power of 2 is definitely equal to 0, and identity matrix to power 2 is of course equal to itself. So these are the trivial idempotent matrices of all orders. So can you cook up a non-trivial idempotent matrix? So think about this problem for the next time. I will ask you next time. Okay. If you don't have any questions, we can stop this meeting here, and I will meet you in a few moments for Math 5. Okay, so thank you for listening.